Hi, today the topic is decoupling capacitors. Why decoupling capacitors? Placement of decoupling capacitors. Trace inductance. What value of decoupling capacitor to be used? How to damp ringing effect. Why decoupling capacitor is used? It is used to avoid switching noise on power rail. So let us consider an example. We have an voltage regulator IC. It generates 5 volts output at Vout pin, and this is connected to VIN pin of IC100. In an ideal case, the trace between Vout pin of voltage regulator IC and VIN pin of IC100 is ideal and it has no inductance. In this case, the IC100 is drawing switching current, that is, the current is increasing from 0 to 100 milliamps and decreasing from 100 milliamps to 0 with a certain rise time and fall time. And when we measure voltage at VN pin of IC100, we see constant voltage of 5 volts. However, if we consider a real PCB, the trace between Vout pin of voltage regulator IC and VN pin of IC100 has parasitic inductance. This parasitic inductance increases with the length of the trace. Longer the trace, higher is the parasitic inductance, and shorter the trace, lesser is the parasitic inductance. Hence, in the circuit, I've added inductor L, which indicates the parasitic inductance or trace inductance. We know voltage across the inductor is given by L equals to di by dt. Since the VN pin is drawing switching current, the current through the inductor will also be same switching. There are two conditions. When the current increases from 0 to 100 milliamps, we see a negative spike at the VN pin of IC100. That is because di by dt is positive and hence voltage across the inductor is positive, and this results in Vout in Vin equal to Vout minus VL. Hence Vn will be lesser than Vout voltage. Hence we see a drop in voltage when measured at Vn pin of IC100. Similarly, when the current decreases from 100 milliamps to 0, di by dt is negative. Hence, we see a negative voltage across the inductor, and when we measure the voltage at Vn pin, we get Vout plus VL. That is, hence the voltage at Vn pin will be higher than 5 volts. Hence, we see a positive spike. This positive and negative spike seen on the Vin pin of IC100 is the noise seen on the power rail. How to get rid of this voltage spikes at Vn pin of the IC? We can use a decoupling capacitor, and it should be placed very close to the Vn pin of IC100. This decoupling capacitor acts as temporary voltage supply and supplies the current required during the switching current loads. How do we choose the capacitor value? We know Q equals to CV, C equals to dQ by dV, and we know I equals to delta Q by delta T, therefore C equals to I delta T by delta V. We know I is the current drawn from the VN pin, that is 100 milliamps. Delta T is the rise time and fall time of the current drawn, and delta V is the change in voltage expected across the capacitor. This is considered as 0.1, and hence we get C, which has to be greater than I delta T by delta V. And now with the decoupling capacitor placed, when we measure the voltage at Vn pin of IC100, it is free of all the voltage spikes and it is constant 5 volts. What happens when we don't place the decoupling capacitor near the V-in pin of switching IC? The trace between the capacitor and the V-in has trace inductance, and again it results in noise. Hence, we have to place the decoupling capacitor very close to the V-in pin of switching IC so that we don't see any trace inductance. Simulate using LT Spice. 1. Ideal trace, no trace inductance is considered. 2. Trace with the 10 nanohenry inductance is considered. 3. Trace with 10 nanohenry and decoupling capacitor of 0.1 microfarad placed near the IC pin of IC100. 4. Trace with the inductance of 10 nanohenry, but the decoupling capacitor is placed far away from the IC pin. 5th, effect of damping resistor to dampen the ringing effect. These are the waveforms. I R of man is the current drawn by the switching IC. So current increases from 0 milliamps to 100 milliamps and again reduces to 0 milliamps. V in 1 is the voltage in the ideal case where no trace inductance is considered. V in of 2 is the voltage at V in pin when trace inductance is considered. We see spikes in voltage which goes until 6.3 volts and 3.3 volts. Which third case, V in of 3. In this case, a decoupling capacitor is placed very close to the IC pin. Hence, we see a very small voltage spike which goes only up to 5.034 volts and 4.968 volts. In fourth case, the decoupling capacitor is placed far away from the IC, and here we see voltage spike which is going up to 5.7 volts and 4 volts because of the inductance present between the capacitor and the IC pin. Fifth, we see the effect of damping resistor. Let me zoom the waveforms. So we see in V in of 3, when we place a decoupling capacitor near to the IC pin, we see ringing effect. This ringing effect can be reduced by the damping resistor, which is given by root of L by C. And in voltage waveform 5, we see no ringing effect.